Section 3.5 is titled Limits at Infinity. And some of this is going to feel a little bit like what we did before, but what we're going to end up doing is we're going to end up talking about what happens on the ends of a graph. So limits are coming up again, but instead of talking about the limit as a specific number, like as x approaches 2, we're going to talk about what happens as x approaches, say, infinity. So we're going to let L be a real number, and the statement limit as x approaches infinity of f of x equals L means that for each epsilon greater than 0, there exists an m greater than 0, such that when the function value and the limit are close, right, less than epsilon apart, that happens whenever x is greater than m. So a picture might be helpful to just sort of talk about what that's happening, and we'll just draw a basic graph of a line, which will work just fine to reference this. So we'll draw this line like so. Hang on, let me draw this line later. Let's do a different graph. We'll do the graph of y equals 1 over x. That'll be a good choice, actually, for this discussion. All right, so the graph of y equals 1 over x looks something like this. All right, so if we were talking about the limit of this, we'll call this f of x. Okay, the limit of this as x approaches infinity. The idea is that we would have increasingly larger and larger and larger x values that we were plugging into the value 1 over x. So at some point, you can imagine that there is this point over here. We're going to call it m. And for all values that are bigger than m, the value that we're looking at for the function value, right, 1 over x, and the value that it's approaching are close together, very, very, very close together. So, within epsilon of each other. And on this one, we would say like that the limit equals 0 because that's the value that the graph is approaching if we traced along this graph as x approaches infinity. Okay, we could even talk about negative infinity and do the same thing right over here. Negative infinity would also happen to be on this one 0. So rational functions are a really popular one to look at for something like this. If we were looking at a graph of a line, we would run into a slightly different sort of problem. So when I draw that line one that I tried to draw before earlier, so we have some sort of a line over here. The problem on this one, of course, is that if you go to infinity, x approaches infinity, this graph just keeps increasing forever, right? So this is something like maybe y equals x plus 3. So as you put in increasingly larger and larger and larger values for y, it's just going to get increasingly larger. It's never going to actually sort of taper off, level out, approach an asymptote or anything like that. So if you were looking at this one, you actually have a limit value. I'll call it f of x again. This limit value is actually infinity because the graph never does approach a specific number. It keeps increasing forever. And if you were looking at the left-hand side and you were going down forever, and you talked about the limit here as x approaches negative infinity, this one happens to go down forever, so the limit is negative infinity on that one. So we can actually talk about the second statement here. I kind of haven't really mentioned it yet, but it says the statement is the f of x equals, of the limit of f of x equals L, means that for every epsilon greater than 0, there's this capital N, such that whenever x is less than n, we can actually look at the left-hand side of this instead. So there's a lower value instead of an upper value that we are talking about here. There's a typo missing there on that one. It should say the limit as x approaches negative infinity, of course. All right, so that's a negative down there. All right, so some of what's going on here happens with these rational functions we mentioned. So if r is a positive rational number and c is any real number, and we have a function that looks kind of like that 1 over x. So we're going to try to generalize it to being c, so any number on top, so it can be positive or it can be negative. And the denominator is x to the r, and r is a positive rational number. So it doesn't even have to be a whole number, but anything that's positive and rational. So, it could be x to the 1/2, it could be x to the 0.2, it could be x to the, it has to be positive, but x to the 4.7, anything sort of weird we'd like that. It could be also something that's a whole number, like, x squared. So anytime this happens, the limit is actually equal to 0. And the basic idea is that the graph you get looks something like the graph 1 over x, if you look at the right-hand side of it anyway. So you do have graphs that they taper off at x equals 0. And if you look at the negative side, the same thing happens if x to the r is defined when x is less than 0. If you can talk about the limit as x goes to negative infinity, then c over x to the r is also equal to 0. So this tells us a lot about the values when you go to the left and to the right of any rational function. All right, so we're going to do a couple of examples. I missed a slide in your notes. The slide that I missed, I'll just talk about it. I'll add it into here later. Is the horizontal asymptote. So in between those limits at infinity and the limits of the theorem that I just had, is horizontal asymptote. So horizontal asymptote is the line y equal x of the graph of f of x when the function as x goes to negative infinity is actually equal to L, or x goes to positive infinity is equal to L. So that's, in this case over here, the horizontal asymptote was y equals 0. And that was the horizontal line that the graph was approaching on the ends of the graph. Oh, okay, yeah, there we go. All right, so let's do an example. That was just a definition that you've probably not seen defined that way before, but it is what a horizontal asymptote looks like in terms of limits. All right, so if you take a look at this function, they're actually wanting us to find the limit as x approaches infinity of h of x, and they give us the f of x function, and they're telling us that that is going to be divided by x squared. So in some sense, the h of x function looks like that 5x cubed minus 3x squared plus 10x, and divided by x squared. Now, if you'll remember from algebra, if you got the common denominator, so distributed the common denominator, something like that. We've talked about this, but it's been a while. You can write each of these terms individually over the denominator, so something like this. And then you could reduce or simplify to lowest terms what you have here. So if you have this going on, we can simplify our function to, 5x cubed is going to be 5x when it's divided by x squared. 3x squared divided by x squared is minus the 3. And then on the last one, we have 10x over x squared, so this is going to be plus 10 over x. And this is what we want the limit of. So we want the limit as x approaches infinity of 5x minus 3 plus 10 over x. Okay, so the 10 over x is where I want to start actually my focus. 10 over x is actually coming back over to here. C is 10, and then the r value is 1. So this fits the description of c over x to the r. So what does that mean? Well, actually, anytime you have something like this, this one's telling you then that this one goes to 0. The limit of that is 0. The limit of 3 is 3. No, that doesn't change. And then what happens on the f5x graph is much like the line graph that I drew to begin with. If you put values getting infinitely and infinitely larger, this one goes to infinity. So the limit on the first piece is infinity. The limit of 3 is minus 3. Well, if you take something infinite and you subtract 3 from it, you still have something infinite. So the limit here is infinity. Oops. Okay, next one, very similar except that we're dividing by x cubed, and I want to show you that it really does matter. That slight change there is going to change a lot. So we're going to divide each one of these by x cubed. I'll avoid writing out the step where they each are individually divided by x cubed. I think you guys can see that okay. So when I do 5x cubed divided by x cubed, that gives me 5. If I do 3x squared divided by x cubed, that gives me 3 over x. And if I do 10x divided by x cubed, that gives me 10 over x squared. So this is my new function. And I want the limit as x approaches infinity, that's better, of 5 minus 3 over x plus 10 over x squared. All right, so just like before, any of these values that are over x, these approach 0. So 3 over x, that's 0. 10 over x squared, that's 0. And if you had 5, say, over x, that would also be 0. This 5 isn't over x. So if you just have 5, it's a constant, and it just stays 5. So sort of there isn't like, what it looks like is there isn't anywhere to actually plug in infinity with the 5. So we end up with the constant that's already there. So this is just the limit. The limit of this is just going to be 5. All right. Now, this one looks a little bit different because the denominator has more going on in it than just a simple x. So I'm going to show you sort of a trick to think about these. What you want to do is you want to identify where your x value has the biggest exponent. So in the denominator, you'll notice this is 3x to the third. So what we're going to do is we're going to multiply by the value 1 over x cubed. And if I do that in the denominator, of course I have to do that in the numerator. So every term is going to be multiplied by the reciprocal of x cubed. So as I do this, this is just a basic trick of limits as you go to infinity. You're going to end up with a lot of things that are over x to the third or over x to some power. So this is 3 over x cubed minus, and now I have 2 over x cubed. Well, that's the same thing as 2 over x squared. Then I have 3x cubed over x cubed, that's the same as 3, minus 1 over x cubed. And of course, the reason and the benefit and the why we wanted to do that is because a lot of these things will go to 0. Anything that's left over x to some power goes to 0. So in some sense, I'll write them all out here just to be really clear and you can see them. This says 0 minus 0 over 3 minus 0. Right, because 3 is a constant, everything else is zeros. Well, when I do this, I get 0 because I've got 0 in the numerator, 3 in the denominator, so this limit is 0. Number 3 feels like number 2, of course, but it's got this square root thing going on. Well, if you want to imagine like the square root of x squared, that's the bigger value underneath that radical. The square root of x squared is essentially 1 over x, or is essentially x. So essentially I've got, if you ignored the minus x part of it, x in the denominator and x in the numerator. So what I want to show you is that means that the highest power is actually x to the 1. So we can multiply by 1 over x. Now, it'll be a little bit more helpful and thought-provoking to write this instead of 1 over x as 1 over the square root of x squared in the denominator, because the square root of x squared would be also 1 over x. And I need this to be in and under, if you will, a denominator for it to make sense. So as I'm looking at this one, the numerator, of course, is 1. The denominator, basically what we have is we have the square root of x squared over x squared minus x over x squared. So, the distribution of that allows the x squared to go underneath the radical that's already there because it's also underneath a radical. So just a few more simplifications here. So the denominator, so I've got 1 over, and then this would be the square root of 1 minus 1 over x. And again, you've got that 1 over x now. Yeah, it's underneath a radical, but it doesn't change the fact that when you have the 1 over x as x goes to infinity, this approaches 0. So what I really have then is I have 1 over the square root of 1 minus 0. Of course, square root of 1 minus 0 is 1, and 1 over 1 would be 1. So this limit is actually 1. All right, one slightly different one now with sine. What you'll remember, interesting fact about the graph of sine, is the graph of sine or cosine, either one, is a trapped graph, right? If you think about the graph here, it's trapped between the top value of y equal 1 and the bottom value of y equal -1. So in some sense, you can write that 1, -1, is less than or equal to the sign value. And you can use the sign value that we have in our function because it's true for any sign value, and it's less than 1. So this is actually something that we're using something called the squeeze theorem. Basically, we're giving an upper end and a lower end to a value, and I'm going to take limits on these things so that as I do that, I end up having something that will be squeezed in the middle to do what I want it to do, or to show what I want to show. So if you take a look what I have so far, I know that the -1 is less than or equal to sine of 2x is less than or equal to 1. That's just a fact about trig functions. They're trapped between -1 and 1 for sine values. And then what I'm going to do next is try to make it look a little bit more like my function. So my function actually has something over x. So I'm just going to divide all sides of my function by x. And this keeps the inequality the same because the x values are positive. If I were looking at this as x goes to -infinity and I divided by x, I'd have to switch to the inequality symbols, right? Make them greater than or equal to symbols. So far this looks pretty good. And then again, we're going to do the same thing by using the limit. So we're going to introduce the limit on each piece. So this is the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of sine of 2x over x is less than or equal to the limit as x approaches infinity of 1 over x. So why do we like this? Well, we like this because, of course, the limit on the left as x approaches infinity of -1 over x, that's 0, right? Because this looks just like the other ones we were dealing with when we were getting 0. So this is 0 on the left. We're going to talk about the middle in a minute, so I'm just going to rewrite it for now. I mean, that's what I'm supposed to be finding. On the right-hand side, we have another limit as x approaches infinity of 1 over x. So something, again, of that same form for rational functions, and this would, again, be 0. So what we're saying is that 0 is less than or equal to something is less than or equal to 0. The only number that will make 0 less than it and 0 greater than it is if it's 0 itself. So this must have a limit of 0. And if you sort of imagine you're trapping something between -1 and 1 and you're dividing by something infinitely larger, it does make sense that the graph would taper off. So if you imagine basically it's doing a wave where the wave is getting narrower and narrower all the way down here, something like that would be your image that you're getting for this. But the squeeze theorem shows very nicely why exactly it gets trapped between 0 and 0, so it itself must equal 0.